Okay, so this last section will go a bit more towards study design. So ideally, how you should, before you get to the point, I have all this data, what do I do with it? If you can make some decisions about how you should conduct your animal tracking project. This part is very much in the beginning of its life, and we'll use a Shiny app I designed that hopefully will run and not crash immediately on every single one of yours computers. But we'll see how it goes. But yeah, so I'll go over just some general recommendations, some general knowledge that you need to not go fully in blind to what the Shiny package is doing. So this is the general workflow of a animal tracking project. From the beginning of, you define a research question, you identify, what spatial temporal scales you want to look at, and any metrics that you want to consider. Right? If you just want short behaviors, or if you're looking at home range, or if you're looking at even bigger large scales than that, and then you typically define what the sampling regime is going to be. You collect that animal tracking data, and then you analyze that data and assess any conclusions that you get out of it. Obviously, this process is dependent on the cost of devices. And the cost of sometimes field assistance or anyone in the field, any related funding that you get. Sometimes you have a really big question, really nice question, and then in reality you can't really answer it. That has happened to all of us, so don't worry about that. We've all been there. And then any sort of challenges in deploying the devices, and any technological limitations that can obviously constrain the study design. So what happens a lot is that people collect animal tracking data and then they're like, okay, now I'm going to define my research questions. What can I do with the data I've already collected? So I think this quote applies very well to that. To consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. You can perhaps say what the experiment died of. I think again, we've all been there. So obviously, and it seems like you're getting this a lot from a lot of different people that have taught this course, is that you want to know what your research question is and what you're looking for, right? This is very important if you're looking at space use, if you're looking at movement behavior, if you want to look at behavior states, if you're interested in collective behavior and interactions. This is all going to influence how you collect the data, how much data you should collect, and if you can actually answer whatever question you define in the beginning. It's a solid foundation to a successful animal tracking project. Starts by this point. Because if you don't do that and afterwards you're like, okay, space use would be nice, but then you didn't collect enough data to answer that. So if you're looking at home range estimation, right, so the lifetime range of all its normal behaviors, all its normal activities, we want to know, okay, so how can I actually know beforehand, before I collect my data, what is enough to see this process? Right, so if you have, this is just an example from a just lifetime tracked stork. So it was actually tracked from 1994 to 2006, so a good sample for what this animal was doing. But again, it's not like you're going to have this every time, like really detailed long-term data for a specific individual. You also have to consider that the resolution of our data, so not just the total duration, but the resolution is important. and you could miss out on the behaviors that you're trying to evaluate or detect if your resolution is not at the right time for that. So this is just an example from this paper in Science from Nathan 2022 that goes into a lot of detail about what we can do with the big data that's coming out of movement ecology. But if we have here, for example, let me fill the little. Okay, we have here, for example, the question was: are shy birds less explorative than bold individuals? Right. So if you have a resolution of 5 seconds, and you can see that the shy individuals were not really exploring their habitats as much as the bold individuals. But if you then would only collect data at a low resolution, and this is just 30-minute intervals, you would miss out. So you would think, oh no, they actually are pretty much the same. So in the second case, we can have, for example, like do these fish are avoiding the fishery vessels throughout the landscape? And the same thing with higher resolution, we see that they are actually avoiding the vessels. But with low resolution, again, with 30-meter resolution, it would go through, so you maybe think they are actually not avoiding the vessels, right? So it's very important, and this is obviously not specifically related to CTMM, but just general advice that you need to consider the resolution of your data versus whatever behavior you're trying to detect. So we've already talked a lot about absolute sample size and effective sample size, and that's essentially what's driving this ability to answer our questions. And obviously, it is inherently connected to the sampling duration and the sampling frequency that you collect your data points. So how long are you tracking an animal for, and how frequently are locations being collected? Again, you can do it with long duration, but then you want coarse and low resolution for certain questions. You can do short duration, but fine if you want to specifically detect, you're interested in a behavior that happens within a short time frame and you want high resolution, like we saw in the example before, that you want to be able to detect those small trajectory differences. Maybe you want both, you want long duration and fine high resolution, which I think is what we all initially would prefer. If we can get both is better. And then you can have all the other, the T-cycle acceleration informed tracking regime. So there's lots of options to what tracking regime you can assign to your device or to your data collection. So we already know that we want as many locations as possible, but how much new information are we collecting, and is the data sufficient to answer the research question? So obviously, ideally, what most people want is increase the sampling duration, increase the sampling frequency. But at a certain point, like for example here, with 1 year of duration, one fix every minute, you end up with over 500,000 locations. Again, this is not very realistic. It would be nice to get sampling duration that's high and sampling frequency that's high and end up with a really nice location set, but again, not very realistic what we get in the field. And we already know from what I've mentioned before that this effective sample size for area, essentially the number of home range crossing events that we need to consider, is the important factor of how much data you should collect. So you don't end up with a case that you have an effective sample size of 4 and then you have to do bootstrapping and may or may not work for whatever data you have. And the same thing is true about any sort of estimation of speed. So speed also has an effective sample size, the number of independent locations that actually inform whatever estimates that you get. So often for autocorrelated data, as we've seen, the effective sample size is always going to be smaller than absolute sample size. So maybe those 5 100,000 locations are not that informative, and you don't need to get a huge funding to get all those locations to then answer a question that you could do with less. So this is basically just a summary of an empirical data set that we have access to. This is the paper from Runen at 2019 that goes into a lot of detail about the autocorrelation present in the data and much information is there. So out of 72% of these empirical data sets with over 1,000 total observations, only 4% had an effective sample size over 1,000, and 30% had a effective sample size of less than 30, and obviously the rest between those numbers. So it's very, very unlikely that you'll get a nice, big, effective sample size. And it's very likely that you'll end up here where things are a bit more tricky to design. So obviously there's also the component of what device even to use, right? So many different options these days, and all of them with different costs, different applications, different ways to actually get it running in the field. And I won't go into a lot of or any detail about that, but it's just something that you need to consider. What is cost effective, right? Because the way I have it for the Shiny app does not consider what the cost of whatever method it ends up telling you it's preferred for your research question. So even if it says, look, this works for you and you should do it, and then you're like, okay, I need a big funding source to give me money enough to do that. So yeah. So remember that I unfortunately do not provide information. So regarding particularly GPS or satellite tags, there's always this trade-off between how much resolution you get and how much duration you get, right? So the more sampling duration you want, it's likely that you'll have access to only coarse resolution, versus if you want fine scale, it's probably not going to last as long. This is just the typical process of the battery functioning of any sort of GPS device. So if you are somewhere in the scale, you want to know, okay, do I prefer low resolution but high sampling duration for my question, or do I want to go further here and I want high resolution and low sampling duration for my question? And as we can see, that's curve essentially of that trade-off and how it looks like when we see the effective sample size at those points, right? At essentially long duration versus short duration, low resolution versus high resolution. We can see that at the beginning we have really nice effective sample sizes for area, and we have longer durations, and as we go through that curve, that decreases until it's almost zero. And then the opposite effect happens with the effective sample size of speed. As it makes sense, like we have a coarser resolution over here, so the effective sample size of speed will start at zero, and eventually you have enough fine scale data to resolve speeds, and then you can get it and the effective sample size. So when you want to answer both of these questions at the same time, you can see that you have, if you're lucky enough to really land on maybe it's good for both, or you might land or when it's good for one but not for the other. And obviously you have all the other potential biases that can be introduced, like location error, if the device has an error of 10 meters or 50 meters or even more than that, and how that can influence your estimates. Obviously, if your home range area is very small and the area is very big, it's something that you need to consider. And there are ways within CTMM to incorporate location error that we could potentially go over at some points. But Yeah, it is something to consider, and any missing data that you can get out of it. So that's an important factor of this curve. It's not always going to be exactly perfect if you get here the 40 days of sampling, and it's going to always have the fix for that that you select. And it can always be affected by canopy type and cover, tree density, any sort of weather conditions that we know that affect GPS locations. So there's always a trade-off, right? So if you want something that's passive and you don't need to be in the field running around after animals, and you also want high-frequency data, maybe you have to spend more money. Maybe you can only track bigger animals that can take the devices that can get that data. If you want passive, but you also want cheap, maybe, again, you're missing out on high-frequency data. If you want high-frequency data and you also want it to be cheap, maybe you spend more time in the field running around after animals, getting locations every 10 minutes or whatever you want. So you have to think about what your priorities are. And typically saying, I want as much information, as many scales as possible, sounds very good, but it's not very realistic. So it's more like you have to decide on what is best and gives you more options. But in this case, like I mentioned before, there's typically the acceleration-informed OT cycle. In certain cases, if we can get even sampling, is typically the best. That opens up a lot of opportunities for analysis. But yeah, accept trade-offs and realize that you can't have all the questions. So for example, here we have a simulated tracking data set. It's a new location once per day. And we can see here, if we actually want to resolve and have a higher resolution, we could see that we're missing out on a lot of these trajectory specifics that we potentially would want to consider. This is the same problem that I showed earlier with the shy birds, bold birds, and the vessels and the fish. So it's important to consider that your frequency of data collection could miss movements, and by simplifying trajectories, also simplifying distance moved. And again, in the other side, if you're tracking a data set for 6 months and you're like, okay, this is what I have funding for, or I need to leave my study site for some reason and I can't collect anymore, is this enough for my data? Because you could have the case of if you keep tracking it for longer, the animal would go further in space, and that would influence what you have. So it's missing used areas, right? So the home range estimated from the initial data set versus the whole thing, because again, it wasn't enough. It wasn't range resident by that point. So in this case, we must carefully consider study duration. So autocorrelation, important. It's good information. We're getting a lot of essentially information that's feeding into the movement process, and a lot of information that's there is either position or velocity autocorrelation, or even acceleration autocorrelation. It's simply not physically possible for these quantities to be uncorrelated, right? An animal is as a continuous movement and a continuous velocity and a continuous speed. So can we see these autocorrelations in the data? Because this is what is going to allow us to maybe get information of, is my data set or is my potential tracking regime enough to answer my questions? So I've already gone over this. It's just so you can keep it in your mind again. This position autocorrelation, the home range crossing time, and the velocity autocorrelation, which is essentially the motion persistence of the movement process. These are two parameters that, if we know what they are, or the potential for what they are with our individual, with our species, we can get some information of the effective sample size that we get out of it. Yeah, so this is just the same as before. Again, just in case maybe you forgot what home range crossing parameter was, but yeah, how long it takes to traverse the linear extent of its home range. And again, the bigger it is, the longer it takes, and as we increase this parameter, we decrease effective sample size. And with the velocity autocorrelation, which is the directional persistence, we know that as this value increases, so we start here at 1 minute to 1 hour to 12 hours to 1 day, the movement tends to be more ballistic or more directional, while it's more less linear if this autocorrelation parameter is small. So essentially, how long does the animal persist in its motion? And again, we have access to data from our good friends, the African buffalo. And we can see that this position autocorrelation, although it's some variation in the confidence estimates, is similar-ish between individuals. So we can have some general idea of, like, for this, at least this population, this is where the home range crossing time would end up being. And the velocity autocorrelation, again, this is a different scale. Before, I think, was days, and now it's minutes. There's some more variation, but again, you have to remember that this was mainly data that was 1 hour sampling interval, so the ability to estimate velocity autocorrelation can become more complicated. So more variation with that, but we also have some idea of where those parameters land. And again, you can do it with basically any species. This is the Mongolian gazelle, and you also have some idea of the positional autocorrelation. In this case, if you remember the example I gave a while ago today already, but that they have months of home range crossing time. So, yeah. So you can do this for all sorts of species and get some idea of these parameters and the variation within individuals. And the reason to look at this is that, once again, these parameters will help you inform study design for your next animal tracking project. And typically, analysis that if you're ignoring a position autocorrelation, we are underestimating any methods that does range distributions and home range areas in general. While if analyses that are ignoring velocity autocorrelation, we are typically overestimating occurrence areas from the occurrence distribution. Okay, so we know that this is all related, that sampling duration interval is relative to characteristic, the timescales, the positional autocorrelation, the velocity autocorrelation, and that determines what we see in the data, the effective sample size area and effective sample size of speed. So even if we're dealing with biases with AKDE, and we know that it can deal with unmodeled correlation, it can deal with small sample sizes, and it can deal with unrepresentative sampling in time. It's just because it can deal with those things doesn't mean you should ignore study design. Okay. So this is just basically looking at the different models that we already talked before, and typically what the expected characteristic scales are relative to the duration, and the sampling interval. Typically the OUF here, where we want the position autocorrelation to be smaller than the duration, right? We want more home range crossing times relative to the sampling duration. And we want both the position autocorrelation and the velocity autocorrelation to be enough to, the sampling interval to be enough to detect those, to be smaller than that. So it can actually correctly get those two values. And because we know that from all of the empirical GPS data sets that we have access to, that the OUF is the more common model being selected. And again, remember the OUF has both velocity autocorrelation and position autocorrelation. Yeah. So this is just going over, once again, our very good friend, the African buffalo. Obviously, we don't have the independent data, so this is what we would like if you would have it. We don't have that. The OUF is the best fit model for this data set. And for example, here we can see that the N area and the N speed are good enough for both home range estimation and for speed estimation. And this is just the parameters that are getting outputted for both the autocorrelation timescales. So we can get both of those estimates, no problem with this sampling regime that we have access to, which is 8 months, so way longer than the position autocorrelation of 11 days, and sampling interval of 1 hour. This is still is enough to resolve the speeds. It's not going to be as accurate, but it's still enough to resolve that. This is just essentially what would happen if we truncate the data, if we make it shorter, and how it would look like. So instead of 8 months, let's do 16 days. And it would be basically, if assuming a Brownian motion process, we have no effective sample size for area, no effective sample size for speed. And this is, if you remember, the integrated OU. So it's basically endlessly diffusive as well, so no home range. But it is enough because it has the velocity autocorrelation, the little curve, to potentially see speed estimation. Though, as we can see, with if we both truncate and thin the data, we might lose on both of those as well. So if we track this individual for only 16 days, and let's say a sampling interval of 19 hours, you'd lose that information. Yeah, so you couldn't use this data for home range or speed estimation. But obviously this is a very extreme example of tracking this animal for 16 days and 19 hours sampling interval. But just so you can see the decay of information that we get out of that. So typically for autocorrelated kernel density estimator, if we want to achieve a relative bias of at least 5%, if we're using the maximum likelihood, we want at least a minimum of 20 for the effective sample size. If we were using the PH-REML, we are looking at a more or less 4.5 minimum effective sample size. And for bootstrapping, we're looking at 2.7. So anything below this, it's not going to be useful for anything, for any method that we can apply. But again, remember of this important fact that you don't want to end up in this position. And we know from simulations, from a lot of simulations, that for the AKDE, if we keep improving the sampling, or if we increasing the sampling duration, we will converge to the truth, the actual true home range, which again we know because it's a simulation, and that the sampling frequency does not matter as much for this, as long as we have decent effective sample size, which is this one. In this case, it's always 30 for all of these. And obviously, as the range crossing time, the position autocorrelation increases, we're going to see less accuracy, underestimation from the AKD. Okay, I really went over this. Okay, so just to visualize it better, with the position autocorrelation as we keep increasing it until we have home range crossing against a simulation of more than 1,000 days, which might not be very common in real data. You'll end up more over here for real data. But you can see that we need more and more study duration if we want to actually accurately get the home range. So if you have a tracking data set with irregular sampling interval, we've already seen you can apply the weighted AKDE. You can also subsample data to exclude closest locations in time if they are not a lot and you know that it's erroneous for some reason. But as a general recommendation, you adjust your sampling duration to ensure data is sufficient to detect this position autocorrelation parameter. Yeah, and as we've seen from the meta-analysis, at least for home range comparisons, you can do it with 2-3 observed home range crossings and 2-3 representative individuals. Not saying you should, but you can. And for speed and distance, which we didn't really cover it, but again, there's an estimator for speeds in the CTMM package, which is this continuous time speed and distance. But the main thing you need to get out of this is that if your sampling interval is bigger than 3 times this velocity autocorrelation, there will be simply no significant signature of your animal's velocity in the location data for you to estimate it accurately over here. But it's just something to remember if speed estimation is your goal. And this is, again, speed estimation purely from animal tracking data. It's not using accelerometers or anything like that. Yeah, so we can see that in comparison, you've probably seen the straight line distance as a method used to calculate distance between. And I won't go into a lot of detail about that, but it's very common in the literature. But you can see that as sampling frequency increases, it actually becomes less and less accurate. The further the higher frequency we collect, while the ST-SD, the CTMM method, actually converges to the truth pretty quickly. And same with the estimated distance traveled from that speed estimation. And specifically in this case, we also want to account for measurement error by collecting calibration data for your GPS error or using pre-calibrated devices, because it's very important. We can see here if even with the CTMM estimator for speed, if it's a model error here in green, it will also do the same thing of simply just not be able to estimate the distance traveled correctly. So there's a data set in the CTMM package for the wood turtles. And you can see that the scale of data that we get, the circles are the errors associated with that. So we have more error than we have the actual locations of the animals. So this is something important for you to consider and make sure you model it in your data. But yeah, but if it's modeled, the ST-SD can correctly calculate the distance traveled by this individual, even with error.
When you're talking about modeled error versus calibrated devices, does that like DOP on a tag? Would that be considered a calibrated device? Or
for the model error in the analysis itself.
Oh, I see.
Yes, yes. Like failing to actually incorporate location error into the method. So as just a general recommendation, if you're trying to detect speed for this estimation, you want to make sure your sampling interval is enough to detect that autocorrelation parameter. So typically smaller than 3 times the position autocorrelation, or velocity autocorrelation, sorry. So as just some general recommendations, it's very important to either collect pilot data or look at any published studies and data sets that you can access to. You want to know what you can expect from the data as much as possible. Obviously, pilot data is not always a possibility, but it does help you to inform your study design. And again, consider the spatial temporal scale and what question you want, because it can influence what you can actually answer with the data set you end up with. And if possible, keep it simple. Use even sampling rates. Don't get too clever with your sampling. You can also try with simulated data first and see what you could expect. You can also divide and conquer, use different individuals to answer different questions. But instead of simulating data, you can potentially use My Shiny app if it works. But obviously, sometimes you must sample unevenly. The idea there is, again, keep it simple. Use no more than 2 different sampling rates. And again, simulate with uneven sampling, see if it still works. Use sampling rates that are integer multiples, because that helps you in the long run if you need to do some different analysis afterwards. Check for artifacts introduced by that uneven sampling. And again, be realistic. No, you can't have all the answers to all the things that you want. And again, collect error calibration data, because you can do location error modeling within CTMM to really incorporate that information and get accurate estimates. Okay, so let's see if the app works. I have some hopes.
It does.
It does work? Okay, well, that's good. Now to see if it doesn't crash on everyone. Okay, so you can either install it with the remotes package directly from GitHub. We can also try running it from GitHub if that doesn't work for you, but try the first one and let me know if that works for you. I'll wait a little bit, and if no one screams out that it's not working, I'll move on. All good so far? No big installation problems? Okay. I'll just start, and if anyone is still not at that point, then you can tell me. But okay, so the main thing to, do I need to increase the size of the text, or is it? Okay. That's true, there's people further away. Okay, so currently, essentially the 2 research questions you can test out. Again, this is all using in the underlying estimation methods CTMM package. So you can do home range, or you can do speed and distance estimation. So we'll run through an example with the home range, which is, again, we'll use the AKDEs and all of the stuff that we have talked about this whole time. You can upload your own data sets, and this is the case that you have a similar species that you're going to work with, or you have data for the study site that you're going, and you already can use that to kind of inform your next project. So basically use information that's already been collected to get that decision making going. You can also select a species from the CTMM package, so you can try once again with our very good friends, the African buffaloes, and see how a project with them would look like if you were trying to answer a specific question. You can also, if you don't have access to any of those, or it doesn't represent what you want to look at, you can simulate from scratch. So a full simulation of a species that you would want to at least behave similarly to your own. That's obviously a bit harder to decide on the parameters there. But we'll try to go just for the selection, because again, it will be easier to run through. So this is just the different tabs, and it's ordered by what you need to do at any point. So you start with the select data. So you have here our list of species available within the CTMM package. So again, I'll go with my good friend, the African buffalo. Why not? So you pick an individual. Ideally, you want one already with a decent. This is the absolute sample size for that individual, and just some information about the interval and periods. So the main idea here is that we'll extract the characteristic scale parameters, the position autocorrelation and the velocity autocorrelation from this individual, and kind of use it to simulate a new animal tracking project with certain scheduling. Yeah. So let's validate first, is just to make sure that your data is enough for this sort of data extraction, and that you have information on the position and autocorrelation. Because again, if you feed in independent data, you're not going to have information on these parameters. And then you extract. So if you go down, once you extract, you can see what the parameters that have been extracted from the individual cilia from this species. So we know the semi-variance associated with this individual, and the confidence intervals as well, the position autocorrelation, and the velocity autocorrelation. And these are the parameters that are going to help us decide, okay, if I want to answer my home range question, how much do I need to track this species for? You can already see also this is the sample size associated with the specific tracking data set. And obviously we want at least enough to extract those parameters. Okay, so now we can decide on, okay, so what tracking regime do we want to try out and see what happens? So let's assume we have a GPS or a satellite logger. I'm not going to select too crazy of a sampling regime, mostly because it might take a while to run and we don't want to be here forever. But obviously, if you're interested, you can do it afterwards and let me know if it runs with no issues. But yeah, we'll start with small just so it doesn't take too long to run. I think we've all been here long enough and we need a break soon. So yeah, let's say 2 months. And this is basically just information to create this curve that I already mentioned or I already showed before, right? The trade-off between duration that we get from a device versus the sampling frequency that we might get out of this device. This is, however, a simulation of this process. It's not like you can say there's a specific model or a model that you can buy, a device that you can buy that will follow this curve. But it's just a good idea to see that you do have that trade-off happening. I'll change it to logarithm scale so you can see these high points first. So we can see like how the duration changes as we have a sampling interval that keeps decreasing, right? So let's do one fix every 2 hours. That shouldn't take too long. So you can select that from the plot. You can also do it manually, so if you have already an idea, I just want to see if 2 months and 1 hour is enough. You can also do by clicking here and set the regime manually. So instead of select from plot. But again, it's your choice there. Okay. So now we'll validate just to make sure everything is going right up until this point. And this is just saying that what your tracking regime will look like. A new location every 2 months for a duration of 1.9 months, around 55 days. Okay, so we'll try running that. It will calculate the runtime of the simulation, which again, if you select, you know, a very high duration, a very high sampling frequency, it will take longer and longer to run. Okay, 2 minutes is not too bad. We can wait 2 minutes. So I don't know if you guys are trying different ones. It might say way more. Yeah. But this is basically doing it with we're not even thinking about into all the detail. We're just picking one and seeing what works, right? Again, remember that you do have some information about the position autocorrelation and the velocity autocorrelation parameter. So we know those values. And we know that by increasing the sampling duration and the sampling frequency and how it influences the values. Essentially, by this point, the main idea is, because we're trying to look at home range estimation, is that the sampling frequency doesn't matter too much about the home range estimate that you get, right? So you don't need to go into super high resolutions to get home range estimation. So already know that from the beginning. Okay, so we can see here, so it already calculated the effective sample size. 8.3, not the best. This is what we could expect from this tracking regime. But let's move forward and just see what would happen with the home range estimate. I mean, you can still, at this point, change it again and see how it would look like with a different tracking regime. But just to save some time, let's just go forward with that. So in this case, we're going to run the estimation of the home range, which is fast because we're not looking at a lot of data here. So we can see what the home range estimate would look like. And the main thing here is you can see that it's very uncertain for this tracking regime, right? With the confidence intervals are very wide. So we're not very sure about this home range estimation. And if we keep going down, we can see that we are expecting an overestimation of this overall of this home range. Yeah, you can also add things to tables and then compare, but I'll just go through it once, and then if anyone has specific questions or things they want to do. Okay, so now we can look at the final report. Okay, so how well was our setup tracking regime at answering our questions? Okay, so this is basically just a rule of thumb, the general recommendation that because of these parameters that we have, we should potentially be considering around 75 days of tracking at least to answer this question. Currently, we are at 55, so that's why we have the effective sample size that's lower. So it doesn't really approach the minimum recommended, but it's also not too low effective sample size that we start being very, very, very concerned. But yeah, so you can also see how the simulation that we just ran compares with simulations that have already ran beforehand, just looking at the distribution of all the potential estimates that we can get from these sorts of parameters. So we see that the current error is within the distribution of values you'd get from these parameters, more or less. though it's for 64 days, so it's a little bit smaller for what we have. But this is what we would expect, right? So the estimated error would typically be around here for that distribution. But it could be worse. It could be even further away, and then you'd be sure that that tracking regime definitely does not answer your question. So currently it's saying it's likely insufficient, mostly because there is some variation within individuals that you'd get, and there's no guarantee that this would be enough to do it. So you'd probably want to do a longer sampling duration to reduce this. So you can, at this point, you could go back and try different tracking regimes until you have something that would be more likely to answer your home range question. Obviously, this is fully dependent on whatever data you feed into it. If the data itself is bad at predicting or estimating these parameters, it's also going to be bad at giving you this information. So you want data that can actually estimate the position autocorrelation and the velocity autocorrelation parameter enough that you can do that. Does anyone have any questions? No? You think this is helpful?
Yeah.
Let me know if it is, and if there's something I can and should add to it. That would be very, very useful. But yeah, so you can also do speed and distance, but I don't know what the time that we have left. I think there should be something soon going on. So we can always talk about it more next week. I'll be around.